What if AI could invent solutions humans can't dream of?
And we thought that we couldn't do any better. There's a heuristic that should be as good as possible. And that's here. We called it the perfect heuristic because we thought it was perfect. But guess what happened? Evolution discovered better policies, better than perfect.
Hello and welcome to the AI Safety Crisis Summit presented by Better Societies, where we explore how to use disruptive technologies to create a future of abundance and solve AI's greatest threats, influencing global powers and our daily lives. Today, we're diving into neuroevolution with Professor Risto Miikkulainen, an AI pioneer, revealing how this cutting-edge method can solve society's toughest problems, from climate change to pandemics. Get ready to rethink AI's potential. Risto is a professor of computer science at the University of Texas at Austin and VP of AI research at Cognizant AI Labs, with an MS in engineering from Helsinki University of Technology and a PhD in computer science from UCLA. He's a global leader in AI innovation. His research centers on neuroevolution and generative AI, tackling decision-making challenges in natural language processing, vision, and societal applications. He's authored or co-authored over 500 articles, including the first ever book on neuroevolution coming out this spring from MIT Press. At Cognizant, he scales these solutions for real-world impact. Recognized as an AAAI, IEEE, and INNS Fellow, Risto's recent accolades include the IEEE CIS Evolutionary Computation Pioneer Award, the Gabor Award for International Neural Network Society, and the Outstanding Paper of the Decade Award from the International Society for Artificial Life. A couple key points to keep in mind is that Risto is renowned for pioneering neuroevolution, optimizing neural networks with evolutionary algorithms to unlock creative, superhuman solutions. He'll reveal how he and his team at Cognizant developed a groundbreaking technology to uncover decision strategies for complex societal challenges. Think sustainable agriculture or pandemic response. What amazes me about Risto is his knack for turning scientific breakthroughs into practical tools that uplift communities and reshape societies for the better. What if AI could invent solutions humans can't dream of? Risto will unveil how neuroevolution is a game changer for building better societies. He'll share the exact same techniques he used to pioneer AI decision-making at Cognizant, scaling solutions in under 5 years that outsmart traditional methods without relying on outdated gradient descent. With over 30 years in AI and 500 publications, he's distilled decades of research into actionable insights for you. I've seen firsthand how his work inspires real-world impact, and now you will too. In this masterclass, you'll discover 3 key lessons: how neuroevolution works, evolving neural networks to solve problems creatively, why it's a leap beyond standard AI, unlocking surprising, effective strategies, and how you can use Project Resilience, an open source platform, to apply neuroevolution to your own societal challenges like climate mitigation or equitable urban planning. We'll explore real case studies like optimizing land use policies and give you the tools to act. Whether you're an AI enthusiast, entrepreneur, policymaker, or community builder, this is your chance to harness AI for a safer, smarter world. Risto Miikkulainen, welcome to Better Societies.
Yeah, thank you, Adrian. Happy to be here.
First off, in your own words, can you tell us a bit more about yourself and what you're currently working on?
Yes, well, definitely on neuroevolution, but also applying it to building a general tool for decision-making support. So something that can be applied to many different topics. I'll show some slides soon about it. The idea is that we model the world using machine learning, and then we discover how to cope with it using neuroevolution decision strategies. And we're pretty far along with it and have several applications already. What I'll show today are some of the pioneering applications, the first ones we developed, and now we try to industrialize it so that it would be possible for anybody who's a little technical to build something. And that's exactly the Project Resilience idea, that people who are passionate about fixing some problems could use this tool and apply it and make a difference.
Excellent. And what sparked your passion for building better societies using AI?
Well, I've been a professor for a long time, decades, and of course, a lot of that is to do something difficult and impress your friends or colleagues with it. But it also seemed like the technology, AI in general, and certainly evolution optimization, neuroevolution, was becoming strong enough that it could actually be taken to the real world and have an impact. And that's what I decided I wanted to do. And that's how I got involved with an industry lab. It was a couple of startups and now Cognizant AI Labs, where we have actually a position that we can develop the technology and then other parts of Cognizant can take it to clients. And we also maintain this AI for good aspect of it, which is really better societies. Like you mentioned, pandemics, climate change, healthcare, optimizing medical treatments, and so on. And I think it is really exciting time because this has been a long time coming. I mean, I've been in AI for several decades, and now it's so close to the real world that whenever we are thinking of something, we're thinking about how it can be actually deployed. And it can actually make a difference. And it's really exciting time.
It really is. And there's so much happening every day. Can you tell us a little bit about how your work can benefit entrepreneurs, investors, AI safety researchers, policymakers, or government agencies that want to use AI for good?
Yeah. Yeah. So what we're building on is a little different from the standard LLMs that everybody is using right now. LLMs, of course, were the big breakthrough, no question about it, a surprising breakthrough. But it's not all of AI. It's not of everything that AI could do. So we are focusing in particular supporting decision making, exactly those communities and those aspects, perspectives that you mentioned. And the technology underlying that, there's quite a bit of work that went into it. Again, decades of work and lots of papers that have 30 pages of math in it. But you don't actually have to know all of that because we are building tools that should make it possible to build applications quickly and also evaluate whether they are working quickly and modify them and maintain them. So this practical aspect is something new that AI researchers have to start thinking about how we can take it to the real world. And then there are other questions also, like how, indeed, safety, like what could go wrong? And if something goes wrong, how do you detect it and how do you fix it and mitigate it? So those are new issues that have come up and we have to think about. But it is possible. You have to be aware. That's the first step. And then there's still a lot of work that needs to be done in terms of AI safety, but there are places where it can go. So one step at a time.
Mhm. And can you tell us about why is neuroevolution so critical for AI safety advocates and societal innovators right now?
Um, I don't think there's really a special hook for safety per se in neuroevolution, but it is a mechanism that allows us to discover decision strategies in general. And there's really not that many technologies like that that come close. So in that sense, actually, it is crucial. So it is in this area where you want to discover something that you don't already know, like how to cope with the pandemic. That was a big mystery. I mean, when we got into the pandemic, we had very little idea what effects our actions might have. And that's where this technology comes in. It allows you to discover those insights automatically. And that is the niche. That's what powers decision makers and society. And of course, you have to have other aspects like safety. And they, like I said, still need to be developed. But you also always have, in paired with neuroevolution, you have a mechanism for evaluating and predicting how well it works. And I think in that sense, it's in a good position. So you never have to really be blind. You can have ideas of what will happen in the future and how your actions affect that. You can explore counterfactuals, what if scenarios, and therefore convince yourself that the path that you're on is actually most likely to be productive or safe or have a good outcome.
Well, I'm excited. So Risto, please go ahead and share your screen to kick us off.
Yeah, let's get started. Here we go. I will have a couple of demos, so therefore I'll keep the screen kind of live, but we start with a presentation, overviewing some of the technology and these applications that we already mentioned briefly. So that's, and then I'll drag in the demos as we get to them. So this is indeed my background. I'm primarily a professor, but like I said, have been taking technology to the world now for 7 years or so. And that is increasingly integrated a society that way, or community. So academic and the industry research labs, they go to the same conferences, publish papers, they share software. And this is precisely what made the AI revolution happen, that we can build on each other's work. And I've seen that happen. I mean, it wasn't that way just a couple of decades ago, but now if you are in academia, you're also most likely in industry. And that is a really productive way of doing that. So let's start a little bit earlier than today, giving a big picture of how we got here. AI, of course, has been developed since the 1950s, and a lot of people who are getting into AI don't really know this history, and it's not really all that necessary either to understand what's going on today. And we, of course, have to develop new mechanisms to understand the current AI. But there's a lot of good work and a lot of perspective that will become useful when we take these AI systems out to the world and especially expand their capabilities. So early on, most of AI was symbolic systems like logic and rules. And later on, statistics was added, probability theory, things that got a little softer instead of hard, fast rules. And then neural nets came out of that. And neural nets came out a couple of times already in the 50s and again in the 80s and then in 2010s. Now, I've seen many ups and downs in that sense, several. And what's really interesting that now we see an up and then we see another up and then another up. Things just keep going better and better. And that is just wonderful. It was still a surprise that the neural nets worked so well. I mean, we were working on these issues of generalization and language and reasoning in the 80s and 90s with neural networks, and it was so hard. It was so difficult to get them to work. A lot of effort went into trying to do variable binding even, like a duck driving a car, when you've never seen a duck in that kind of a role. And it turned out that we really didn't have anything that was wrong. It was just that we did not have the scale. And million times more compute in 2010s gave us that scale, and things started to work. Things from the 90s started to work, and we got deep learning. And that's great. Everybody's happy who's been working on it, that the ideas worked. But then an even bigger surprise happened in that if you just do something very simple, predict the next word in a bunch of text, and you have all the text that's ever been published to train your network, and you have a network that's now 40,000 more larger than it was just 2010s. General knowledge start to emerge. These neural networks start to be able to answer questions about the world, which they've seen in these examples. And that was a big surprise, an even bigger surprise. I don't think if anybody tells you that this is what we were trying to do, they are lying. This was a surprise for everybody that it happened this way. Of course, we always tried to do it, but it happened as kind of a side effect of something that already existed. For other reasons was a big surprise. Of course, we now have new technology too. Transformers is a very fundamental architecture for neural networks, and we have diffusion nets and even adversarial training and things like that came in the 2010s and so on. But it really was the scale of data and the scale of compute that mattered. Now, the LLMs are still very expensive. It's very hard to build one. You can't quite do it, with your laptop. And only a couple of places in the world can really build these largest models. But what's really great about it is that they are available. So you can interact, anybody in the world can interact with some of the best models that there are, and put them to work. Maybe you have to pay now a little bit to interact with them, but you can build these interfaces, knowledge retrieval systems, and assistance, and reasoning, and writing, math, coding, and that's already very helpful. And there's a lot of work now in putting them together and making them actually reliable and useful to people. But we can also ask, is this it? Is this all of AI? Well, what happened to all of those good ideas that we had in the 90s that are not part of the transformer architecture and LLMs, agents and planning and reasoning and so on in symbolic domains, for instance. And indeed, we are seeing a bit of a transition again, and that is from AI models that predict what will happen to AI models that actually act on the world, do things, change what's happening. And now we start seeing buzzwords that are about agentic AI as opposed to predictive AI. And I think that this is a very important transition. And the AI that consists of agents that do things can be much more powerful. And that is really what I want to talk about today, too. And decision making is really the challenge, the core challenge for agents. They observe the world and they make decisions based on it, and then they take action and change the world, and then they do this again. You are in a loop in that way with the world. And you can have much bigger impact if you have these kinds of AI agents, because you can really take challenging societal problems and try to solve them, find optimal strategies to coping with issues of the day. So, for instance, pandemic response, medical treatments, climate policy, but also really in business, investment marketing, engineering, designing self-driving cars, for instance, and other devices, education. How do you actually train people optimally, and maybe rehabilitate those skills that you might have lost, or reskill people who now have to actually learn to cope with the new world. A lot of
Yes.
jobs will change in the next decade or so. How do you reskill them? We can use AI also to do reskilling optimally. So there's really, sky's the limit. You have to be a little creative. You have to think about what those decision problems are, but we can use AI to help them. So what I'll talk about today is a different technology than the LLMs and the transformers, technology that allows you to discover new solutions, decision strategies in particular. And here's this diagram here is a pandemic diagram. It's predicting what will happen in the pandemic number of cases. And then it's making decisions about whether to close the schools or workplaces or stay home requirements and so on. All the different actions that the government decision makers can take in order to contain the pandemic and have, at the same time, minimal impact on society and economy. It's a very hard decision problem. And we took it head on, and I can show you a demo, hopefully, in a few minutes on how that works. And here on the right is also a rule set representation of something that was learned in the same way using evolutionary optimization, but deciding what kind of medication to give to a patient that has a diabetes and comes to the emergency room. And we can also, in this way, discover optimal treatments that are personalized. So each patient gets their own personalized decision because we've learned that as a decision strategy.
So
And
this is
now,
something.
yep, go ahead.
Oh, I just wanted to emphasize for the audience how important it is to understand this shift change in humanity's history, where for 200,000 years of human history, we've had five major technological revolutions: fire, agricultural revolution, industrial revolution, the internet, and now AI. And a lot of people compare AI to all of these previous revolutions. And I think there's a key distinction here, which you've highlighted, where in the past, technology has always amplified our strength or speed, power, thinking, but it was extensions of us. And now it's actually for the first time in human history where these technologies will actually make decisions for us. They will have their own agency, and it will be up to humanity to decide to trust these technologies. And so getting it right and having the data and the thinking to explain how they're coming to these conclusions and how they're being trained is really important.
Mm-hmm. Yeah, absolutely. And then I think that you can still view AI as in service of human decision making, that there is still, at least in the near future, a human in the loop that's evaluating what these decisions are. So it's like having a really intelligent assistant, something that doesn't miss anything, whereas a human decision maker might have biases and might miss something important because there's just so much data that humans cannot handle it anymore, but AI can. But it's still empowering human decision makers. I like to think of it as the humans still set the goals, the objectives. What do we want to achieve? And the AI comes up with trade-offs, potential solutions that then the humans will pick from based on their value system, the goals that they decide are most valuable. And that is the role of humans. But it is very much in service of humanity, even though its role has expanded. But it allows us to be more effective in what we do. Right. Okay. So let's look at this new technology, discovering new solutions. And I also want to make the point that it is not going to replace LLMs. It's going to be this kind of applications of this new technology will require many different technologies and their confluence and their integration in order to be effective in the real world. So LLMs, of course, play a large role in talking to people and explaining what's happening, asking what needs to be solved, and so on. It gives us still the interface, but the core is now this neuroevolution technology. That's actually a big diagram about a system that we have built at Cognizant AI Labs for doing decision making. And the one reason why I want to show it is exactly this orchestration that in the beginning here on the left, you start with LLMs. The decision maker might talk to the LLM about what the problem is. An LLM can help identify opportunities for AI-based decision making for an organization, whatever it is. It might be a hospital, it might be a food distribution center, or it might be a business. What can we do with AI that improves the operations of that? And we can use LLMs to also clean up the data, even create synthetic data if you like to try it out before you have real data. But with real data, you can use LLMs to find mistakes in it, fill in missing values, make it more consistent so it's easier to learn from. LLMs are really good at that, preparing the data. And then you have, so that's the LLMs. And also you have something in the output when you are actually asking LLM to give you suggestions, and it does, you want LLMs to explain what those actually are, why these are good suggestions, and what are the consequences, what are the risks and potential pitfalls. LLMs are, again, very good at that. So this is now really important that we have LLMs on both ends where the core is maybe a different kind of AI, but LLMs make it possible to deploy this AI so that humans can trust it. And they are, first of all, they're solving the right problems, and then humans can actually then deploy them and understand what they are doing. But in the middle here is really the heavy lifting what happens. We have predictive and prescriptive machine learning. So we have still machine learning that predicts. It's a surrogate for the world, so that we can, with this surrogate, we can learn what decisions to make. We are searching for good decision strategies, and our surrogate evaluates and tells us which ones are the good strategies before we deploy them in the world. And we also need this trustworthiness evaluation. We need to be able to evaluate confidence and uncertainty on the predictions. So if, for instance, we make a decision and we estimate that the patient will recover with certain probability or have certain side effects with certain probability, we would like to know what the confidence estimate around it is, so that we can choose something that maybe riskier, but has still even with the confidence estimate is likely to be worthwhile. That's important. That's technology that exists just for that purpose, estimating confidence. We'd like to also be able to explain. Now, if we have neural networks, they are great at learning, but they are opaque. We don't usually understand what's going on. So we need to develop something like a rule set that imitates the neural net and is explainable. Explicit rules. We can see them and with an LLM explain what they mean. So all of these elements are needed, and they are different technologies, but they do come together so that we can have actually a decision-making system that can be deployed, understand the problems, utilize data that's available, estimate how reliable your solutions are, come up with suggestions, and then explain why those are good suggestions. So that's a big picture of this. But I'd like to focus now today in the middle here, where, like I said, the heavy lifting is done with this technology that's not LLMs, but it's machine learning and two different kinds of machine learning techniques. The prediction is pretty standard. That's what we've been doing, and that's deep learning, basically. We are creating a digital twin of whatever the domain is. If it could be a digital twin of a patient, for instance, or digital twin of a market where we are trying to have an impact. Or it could be even a simulation like a physical system. If we are trying to design a better gas turbine or something, we could simulate it. But the idea is that it is a digital twin of something in the world that we want to optimize. And most often today, it is some kind of a database system, a machine learning system. Simulation is really good if you can do it, but understanding the physics is often hard. And if you are talking about society, understanding what people do from first principles is not really quite possible. It was possible in Asimov's Foundation trilogy, but not in the real world. So we instead use deep learning and build a model based on data that we observe in the society, and then can predict what will happen when we make certain decisions. All right, so that's the prediction. But the prescription is where the real meat is, searching for good strategies. So let's take a look at that. That's where neuroevolution comes in. So discovering something you don't know is a search process. Now, deep learning, LLMs even, they are trained differently. They are not through search. It's gradient descent. And that means you do have a gradient. You know where you're going. You know where you should be going. You follow the gradient and your performance will improve. That's because we have data of situations and the correct optimal outcomes, the decisions that need to be made, or the predictions, what the outcomes actually were. So we have systematically collected this kind of supervised training data, and we can train a deep learning network or an LLM that way. But what if we don't know? Like, what if you're playing chess and you don't know what the optimal move is? Or you are a robot and you're trying to move around in an environment, minimizing energy and not bumping into anything, and your actions to your motors are not known, what the optimal ones are. You have to search for them. And you try something out, and you see what the outcome is, and then you take that into account. That's either good feedback or bad feedback. Good feedback, you try more of that. Bad feedback, you try something else. And this way you're doing search. It's not systematic search or random search. It's an intelligent search because you do take the feedback into account. So reinforcement learning, for instance, another area of AI, is like that as well. So you are still you have one individual and you're gradually modifying it, but you're modifying it so that you are maximizing your reinforcement. That is one way of thinking about what the search process is. You try to modify your solutions intelligently and get better, even when you don't know where you're going. You don't know the optimum. You're searching for it. Now, that's great. So that's one element. We have a search process that is trying out alternatives and tries to find good solution strategies. But we also need a surrogate model. In almost all applications in the world, you don't want to try your intermediate solution strategies in the world itself. I mean, if you're looking for a good medication for a patient, you don't want to try just any medication on the shelf on real patients, or trying to learn to drive. You don't just do actions and see what happens. How often do you crash? You built a surrogate that predicts what will happen when you act according to your strategy. And you have to train it. You have to collect some data. And here in this diagram, this kind of crystallizes that. So we are looking at a decision situation. Maybe a patient comes in. That's the context. You have to make a decision what to do with this patient. And then you produce an action. Give him medication X. And then you do that and you observe the outcome. This patient with this medication recovered this completely and quickly, for instance. That's your data point. And you collect a lot of data points like that, and you do have a supervised training set. And you can train a predictor neural network using deep learning with that kind of data. And that neural network is your surrogate model for the world. You no longer have to go and try out the actions on real patients. You can ask the predictor, okay, given this context, here's what I suggest. How well would that turn out? And this becomes feedback for your search for a good decision strategy. And that surrogate model is important. It allows us to really hyperscale the search for good solution strategies that we wouldn't otherwise be able to do. And therefore, to crystallize this again or summarize, we have one model that tells us what will happen. And then we learn another model that tells us what we should do about it. So what will happen is the surrogate model. What we should do about it is the neural network that was found during search, found using Neuroevolution. Okay, so let's look at now a little bit of what Neuroevolution is about. I mean, we're not going to do a deep dive into technology. If you're interested in it, I have the references in a bit. But what is this Neuroevolution and in general intelligent search? Now, you can do search using reinforcement learning, but like I said, you have a single individual. And therefore, you're trying to more or less feel what the gradient is around it. Even if you don't really have the targets, you can try out different things and see which ones result in better outcomes. And therefore, you can estimate the gradient and improve your individual. But population-based search is distinctly different from that. Population-based search like evolutionary algorithms. And the idea is that you have an entire population of solutions, not just a single one, but hundreds of them. And they're all different. They are very diverse. And you evaluate each one of them. So you have an encoding of a solution. You decode it into a neural net. This is like DNA. It could be a string of numbers that code the weights of the neural net. You decode it into neural net. You run it in the environment, measure how well it works. You get that feedback. We don't know the target. We don't know what the network should do, but it does something, and we measure how well those actions work. That becomes a fitness of that genome, that population member. And we do the same for everyone in the population. They are all tested, and we have now an idea how well each one of those works. And then we throw away the bad ones, we keep the good ones, and we run crossover and mutation, these genetic operations on those good individuals. And that's what makes it an evolutionary search algorithm, a population-based search algorithm. So simple operations are depicted here. You have two parents. You pick the ones that are really good in your population. So the parents are already known to do pretty well in whatever it is, prescribe good medicine or drive the car well or whatever. And you take part of the encoding from one parent and the rest of it from the other parent. And that's how you get offspring. They are recombinations of the parents. And this is where the biological motivation comes from. I mean, this is biology. You get a recombination of genes from your parents. And therefore, offspring is a combination of the parents. Now, what happens in this computational evolution is that you always throw away the bad ones and keep the good ones. So some of the offspring are good. Some of them may not be as good as the parents. That's okay. We just throw those away and keep the offspring that are good. And that's precisely what evolution counts on. That sometimes you get lucky in that in this crossover, you combine the good aspects of both parents in one of these offspring. And therefore, you make progress in discovering better solutions. And it's perfectly fine to have some offspring that's not good, individuals in a population that don't turn out all right. We just throw them away and try again. And it's worth it, even if they are 100 times more prevalent than the good solutions, because every now and then you find something good. And that is important because it allows us to explore. We can try out solutions that are really different from the parents, for instance, that are in completely different parts of the solution space. You can't do that in reinforcement learning because you have an individual solution and you always try to make it a little bit better, a little bit better. In evolutionary optimization, population-based search, you can spread out your solutions all over the place and really explore and try out wild ideas. So the amount of creativity is magnified in population-based search. And that's how you can find solutions that are surprising and effective. And that's what really draws me into the evolutionary optimization. That's what finding these things that are surprises. It always gives me a kick, and evolution is a really good method for doing that.
So,
All right, I
Risto,
have to mention. Yeah, go ahead, Adrian.
if I think you're going to be diving into this with some of the examples and demos, but for the listeners to clarify, my understanding is that the inputs are any type of data, and you want to see as many of the possible combinations simulating what evolution would do over hundreds of thousands of years instead in minutes or seconds, right? And that crossover of every possible mutation or combination would allow you to see the widest spread of possible variables and outcomes and how they played out in the given virtual environment to test their abilities. Is that right?
Yes. Yep, that's exactly it. That's exactly it. So when you say that it's search, people think that, oh, what a waste of time, because you're just searching. But the idea is that it's not actually a waste of time completely, because this search allows you to be creative and find surprises. And I like to illustrate it with this little diagram here on how it works. So I like to think of my search space as a table surface. And my solutions as points in that surface. So any point in this area here is a potential solution, like a neural net, a decision strategy that expresses a decision strategy. And when we first create the population, we want it to be very diverse, cover the whole space. And even if some of those are very strange solutions, they're still in the space, so we want to cover it. And then we evaluate. Every single one of them is tested in the domain. And here the size of the dot indicates how good they are. So the small dots here are going to be thrown away. They didn't work out. They were not good individuals. But there are a bunch of these here that are actually quite good, pretty large. Each one of them then decodes into a neural net. And we pick a couple of those large dots and their neural nets, and then do a crossover and mutation on them in order to hopefully get an offspring that combines the good aspects of both parents. And then we mutate just in case we don't have all the right weights. We also have mutation that does this kind of a local search around the individual. So we create a couple of children here, and parts of it comes from parent A, parts of it parent B, and then some random mutations. And we do that many times so that we fill those slots of the bad individuals that we thrown away and keep about the same size population. But now this is no longer really covering the whole space, because we know that these solutions over here are not so good. These solutions over here are not so good. We have more solutions around the good individuals, the parts of the space where the good solutions are. And we do it over and over again, over multiple generations, like you said, thousands of years, or millions of years. Usually we use hundreds of generations is enough to get somewhere. And here we have demonstration, I guess, 9 generations. And we see that our population after 9, it's already focused around a couple of areas where solutions exist that tend to do really well. And that's what we want. And you can see that there's really no stopping point. You just have to stop at one point where you believe that you have exhausted this process. Nobody's going to tell you that this is the final best solution that exists. I mean, complex high-dimensional spaces, you never can tell that. But you can tell that your system doesn't make progress. You have a solution that's good enough for what you want to do. And that's when you stop. And you pick some of these, maybe one of them, the one that performs the best. Or maybe you pick a couple of them, and maybe they're good at different aspects. Maybe they trade off some objectives, and you have a whole solution set that you can deploy in different cases. Because you still have the population in the end, but now they are just, most of them are very good. So that's what population-based search tries to find. That's the process. And now the massive exploration, what happens there? So let's just take like a little one-dimensional kind of cutoff of that space. And now the third dimension here, or the height, indicates how good the solutions are. So you want to find peaks. And initially, your population is all over the base, kind of randomly perhaps set, or in some initialization of known solutions. And what you want your population to find are these peaks like this. And that's really what the search will find for you. But notice what happens if you're doing something like reinforcement learning with a single solution. Wherever you start, you make these small changes and you climb the nearest hill. But then it's very unlikely that you'll jump anywhere else in this space, because you are always wanting to modify and improve what you have. But with a population, you have some solutions here. And for instance, maybe you have this one and that one, you do a crossover, you might end up on this new peak that didn't even know existed, but because you make this large jump by recombination, you find that there is a peak there. And same thing here, and that's actually probably the optimum there. So that's how this evolutionary search progresses. It is intelligent in that these combinations of partial solutions give you likely, eventually, something really good. And this is interesting that people have tried to estimate how well does it scale up. So in the lab, K lab, in the Cognizant AI lab, we had Baba Kojad and Horman Sharsa did this study where they were trying to design multiplexer circuits. So electrical circuits that implement electronics, implement multiplexer design. I mean, you can build it from first principles, but it's a very hard search problem if you try to just search for the circuit. And it turns out that they could. This is actually John Kosa proposed it a long time ago, but now with more modern search mechanisms, we could push it. And they actually solved a 70-bit multiplexer design, found functional multiplexers 70 bits wide. And that's a search space that's estimated to be 2 to the 2 to the 70th. That's the number of possible circuits. And you're trying to find in this 2 to the 2 to the 70th circuits ones that work. Now, how big is 2 to the 2 to the 70th? I mean, it looks pretty compact, right? Well, if you express it as a decimal number and print it out on a piece of paper with a 10-point font, it takes light 95 years to go from the beginning of the number to the end of the number. And that's the number of states. so it's really hard to even imagine something that big. How can you find a solution there? That's because you can find some partial solutions. Good genes, they do maybe some of those multiplexer cases right, and then another one that does other cases, and with recombination you do more. And this way you can actually find solutions in a space that large. So it's an intelligent search that every part of, it's not just parallel searches in different parts of the space. No, they talk to each other. And if something is found here that's useful, it may recombine with another solution and get a really big leap forward that way. And that's what makes population-based search, evolutionary search work. All right, there are a couple of other challenges. Another one is dimensionality. Like, how many knobs do you have to turn at once in order to find a solution? How many variables do you control? You know, it's not just that you give one medication. Maybe it's medication and its dosage and a sequence of those, and maybe another medication at the same time, and lifestyle changes and all kinds of things that interact at the same time. And your recommendation consists of a suggestion for each of those dimensions. Now, when humans think about a problem to solve, they can usually handle about 7 plus minus 2. That's what you learn in psychology class, 7 plus minus 2 variables. Methods like Bayesian optimization can do about 10, maybe 15, and now there are new methods that scale it up a little bit more. Now, Kalen Deb did a study where he really tried to push evolutionary optimization to very high dimensional spaces, and he was working on a metal alloy manufacturing process, so multiple stages of melts and how you use your raw materials in order to get the products that you need. And he was able to push it to 1 billion variables. So you have a billion knobs that you're turning at once. That's a little bit beyond what people can do. And that's exactly what I was talking about earlier, that now we can use these tools to help human decision makers who cannot turn billion knobs at once. But they can get these suggestions from AI and then evaluate that, okay, yeah, I like that. I will deploy this solution. Or I want to make some changes because I have another source of knowledge that the AI didn't have, my preference. And therefore I choose something else from the population. But it gives you, evolution and AI will give you the material from which you can make an intelligent decision in spaces that are so large, so multidimensional that you could not really cope with them. All right, so that is an illustration and motivation of evolutionary search, population-based search. And if you are really interested in learning more about it, we are finally done with the textbook that I started thinking about in 2002, but things got better and better, and new technology came out, so we didn't have a chance to finish it until now. And it's coming out within a month or so, in 2025. And there's already a website which we still have to flesh out a bit. There's a bunch of demos there already, and there will be exercises and software so you can get started on it. So this book covers the whole 30 years of neuroevolution, including very recent work where you are combining it with large language models and so on. There's a shorter article that it's a review, came out in Science a few months ago. And I also have tutorial slides and a video and a little exercise that you can do. It's also one of the exercises in the book. And I taught a class. I put together a class, and the material is available in this website if you're interested. I'm thinking of making it an online class as well. So we're trying to promote this because I think that the time is right to take this technology, neuroevolution, and address real-world problems with it. Problems that you cannot really solve in any other way, not with LLM supervised learning or even reinforcement learning. And therefore, it opens up new opportunities. Okay, now examples. The rest of what I want to show are a bunch of examples of how this might work. And we start with somewhat simpler ones, and then we go to big problems in society, where I think we can make some progress as well. So the first one here is something we started with a little startup several years ago, 10 years ago or so, and that is the optimized website design. And that means that you have a web page, and it is something like this. It's for education. It promotes educational programs for people who want to learn a new trade or new skill. And this is, for instance, this page particularly is about medical schools. And explains a little bit of what a doctor does, but then there's this widget here that allows you to fill in a little bit of what you are like, and then it will make some recommendations for you. But the point here is to design this widget so that a person who comes to the site is more likely to click on that action button, find my program. This is called conversion, and the design of this page is called conversion optimization. You're trying to come up with a design so that the users are most likely to press that button. And it could be something general like buy something or find out more or sign up or something like that. It's an action that you want them to perform. Now, there are people who do this for a living and have been for a long time. They call themselves conversion scientists. They try to apply techniques of design and colors consistency and various Gestalt principles to make this really appealing and point that. But we can also design these systems using evolutionary optimization. These widgets using evolutionary optimization. and we tell the system to try out different colors, try out different phrasings, different organization of the page, and so on. And there can be, again, millions of possible combinations of those. Which ones are the good ones? And it turns out that evolution can actually be pretty surprising. Here, if this plays, it's a video. Oops, I can't, it's supposed to play. There's a little video here, animation rather, that shows how evolution searches for these different designs. And I don't quite know why it's not playing. I was playing a few minutes ago, but it is in here, and you would see these different designs flash by as evolution is searching for better designs. But the bottom line is still very visible here. This is a human design by conversion scientists. They are, it looks kind of appealing and nice and elegant. This is a design by evolution, and it looks quite different. While this was going on over 2 weeks, we tried many different designs. Evolution discovered those, and the conversion scientists were looking at it, and they called this approach the ugly widget generator, because to them, these designs looked ugly. They did not correspond to the principles they had learned on and tried to apply, but they used garish colors and really active, annoying statements. But it turns out that these designs, like this one, converted 45% better than this one. So, sometimes humans miss these solutions that actually perform really well because they don't really test them. They use principles that make sense, but they're not the principles that actually allow you to convert better.
And how much
So this
is
is
the
what
data?
evolution. Yeah,
How much is the data synthetic versus traffic to that website and then determined through the
sure.
A/B testing of the evolutionary algorithm?
Yeah. So actually, you mentioned A/B testing. That's something that's a tool in industry. You try one design, you try another one. One is A, the other one is B. You test them, see which one is better. And our slogan was ABs for babies, because this is evolution, and you try millions, maybe not quite in the real world, but certainly thousands of different designs. So it's like A/B testing on steroids. Evolution creates you these alternatives. So this is actually a small enough problem that you can do it live. You can deploy each one of these designs over about 2 weeks. You get over a few days, I guess you get 2,000 different users come to the site, and you can measure reliably enough how many of them convert. And then over about 2 weeks, you find these designs. Of course, the different scales, different problems are different scales, but that's what can be done. This problem can be done live. Now, of course, we developed it further, and we built a surrogate, which then estimated how well something converges. And now you can search a lot. You can really try millions, and you can broaden the search space with that. But the starting point was to actually deploy it live. That's how the conversion scientists were looking at them, because they were deployed. But it does scale up, and this was just to design this widget. But to design the whole page, or maybe multiple sequences of multiple pages in a sequence, that's much larger. And then you might actually deploy a surrogate model to do it.
Yeah, I think, for anybody on entrepreneurship or marketing, you understand the value of this. It's incredibly valuable and would save a ton of time. I think it is really interesting that the solutions tend to be solutions that experts or professionals in the space would say they wouldn't implement themselves.
Yes.
But at the end of the day, right, conversion or data is what should be governing a lot of the decisions.
Yes. This is exactly why I like AI and why I like evolution computation in general. It surprises you. It gives you something more than you can do. And this was not the case for the longest time. I mean, AI was developed just to replicate what you already thought was needed to be done. But now we have AI that goes beyond that. And it can make wonderful discoveries, including things like that. Here's another discovery. And maybe a little bit more consequential for society, perhaps, not just making money, but actually helping to feed people. So this was an application where we were working with MIT Media Lab, Caleb Harper, and in order to come up with growth recipes for agriculture. So actually, this is just for show here. We had an actual closed container for these plants, and we're working with basil. So multiple trays of basil. Each one of those chunks gets a different growth recipe, which means different light wavelengths, amount of light, strength, and period, ultraviolet, not, also nutrients, how much water, what the temperature is. So you control everything in that environment. Now, farmers know a lot about their own patch of land, but what if you could what if you could control everything? Turns out we don't know how we should do it. And that's where we can bring in now this approach of first building a surrogate model by planting a bunch of days with different kinds of recipes. The ones that are known to be useful and ones that are very different from them. And then you build a surrogate model that allows you to predict how well a new recipe would work out. And now we actually have to grow things. So it takes 3 weeks. So we had about 300, I think, real plantings and observations. But then when we have a surrogate, we tested millions of recipes because you just ask the surrogate, you get an answer right away. And something really interesting happened. So this is actually showing an experiment where we were just optimizing the light. So what the light wavelength was, how long the light were on, and how long ultraviolet light was on with the visible light. And initially we had, you set up the search space, and we set it up so that the lights are on from 6 to 18 hours, anything within that range. But it turned out that evolution very quickly discovered that all the lights were on at 18 hours. I mean, as long as they could. So we said, okay, open it up, make a wider search space. And it turns out basil doesn't need to sleep. It thrives when the lights are on 24 hours. It's bigger, the basil is tastier, and this was a big surprise for the experts, the botanists, the biologists. They did not expect this to be the case. That's why we had the 18-hour limit, because plants, most places, not quite in the poles, but most places they experience daylight and nighttime, and it was understood that maybe they need to sleep and rest and something, have metabolism going on. But no, actually 24 hours of light makes them happier. At least they grow better that way. So this is the kind of discovery that could really be consequential. We just missed it because we had certain assumptions that turned out to be not so productive. And if we are actually scaling this up to grow food hydroponically, we'd be well advised to try to optimize the recipes, and there might be surprises there on how to do it well.
Absolutely. And I think just in that example alone, the implications are massive. Just having less agricultural land to use, but more output from every single one based on just optimization of every plant's optimal growth path is amazing.
Yeah, and you can optimize other factors too, like you can minimize water usage if water is a scarce
Right.
resource. So the evolutionary approach in particular lends itself well to multi-objective optimization. So it's not just one thing that you optimize, you also take into account other constraints and other objectives. So it can be more sustainable agriculture as well as more productive.
Right. And that if you're an individual farmer with a permaculture type situation or an industrial farmer trying to maximize output, that means it will apply no matter what your personal situation is.
Yeah. Okay, I have 2 more examples. Now really getting into the society, decision-making in society. The first one is the COVID-19, how to cope with that. And the second one is land use or climate change. And I think that this will illustrate the opportunities there and, really the challenges decision makers communicating to them. I think the technology is quite productive already. So now, yeah, COVID-19. So we needed to make decisions, the society needed, governments, municipalities, of what kind of restrictions to impose. We had no idea early on what was happening. So different places, different countries tried different strategies. And some of them closed the schools, workplaces, like I said, gatherings, travel, mask mandates, contact tracing, all of these were actions that were done around the world to try to mitigate the impact of the pandemic. And that means, number of cases, hospitalizations, and deaths. And at the same time, you'd like to do it so that you disrupt regular normal life as little as possible. But that was not quite true. I mean, life was disrupted, but we tried to minimize that a lot. So again, we apply the same kind of approach. We have a predictive model as a surrogate, and then a prescriptive model to make these recommendations. So you can evaluate how well they would work. Now, here the economic cost is really easy to calculate. Well, it's not easy, but you can see it immediately. You can assign some values, weights on these actions, and then just sum them up. It's the prediction of how the cases will develop, which is more interesting. And there we built, again, a surrogate model and then the prescriptive model. So this was done while the pandemic was happening. We started in early 2020. I mean, I think March and May, and so the first models. And we had the good luck of being at the time when data was available. It came out almost in real time, all around the world. The number of cases was available. But also there was a team at Oxford University that gathered information about the actions. So they coded everything that the government was doing all around the world. Well, some countries maybe not so reliable, but many of them were. And we could see then how did the actions actually affect the outcomes. And we could learn. And we did also, at the end of 2020, we opened it up as an X-Prize competition for anybody to enter with their own ideas of how to predict and how to prescribe, use the same approach of, this approach basically, but any technology, not just evolution, and compete and try to come up with good solutions. So this was a big effort. And at the time, it was a little controversial too. And we didn't really know what was happening, but it was a great machine learning challenge. So indeed, we have these two models. The predictive model is a neural network, and you have a data set. So you can use, for instance, LSTMs, some kind of a recurrent network that looks at the past history of cases and actions and makes a prediction of what the current action will have over a long time. And that can be trained. And then we have an evolution of a neural network that makes the suggestions. So here we don't really have a target, as we talked about it. It's a neuroevolution application. We have multiple objectives. So evolution tries to discover a neural net that makes recommendations that minimize the cases at the same time as minimizing the severity of actions, the stringency of restrictions. And here's a little animation that shows a Pareto front, combinations of these two different objectives, the cases and the cost, the stringency. And what you want is as few cases with as little cost as possible. You want to be down here. And you can see that the population actually spreads out and represents the different trade-offs pretty well. That's what a Pareto front is. It's the set of optimal trade-offs between multiple objectives. And we do get that. And then it's a decision maker's job to decide, well, I really want to minimize cases, even if it costs me a little more. Or economy is important. I can leave it a few more cases if I have less of a cost. So you get to pick. And that's what you would present to the decision maker. Now, what did we find out? I mean, we ran it for almost 2 years, a year and a half, I guess. And indeed, interesting things were discovered. Already in May, our models started to suggest closing schools and workplaces. And this was not common knowledge in May, but it started to come out in the literature and news and everywhere that indeed this is where the contagion happens. People are indoors 8 hours a day. A lot of people get sick that way. And indeed, 2 weeks after we saw it in the models, these papers started to come out and people start to close them or have other mitigations at schools and workplaces. Then in the fall, things changed. Schools adapted. They started putting dividers, ventilation, alternating different students at different days. And schools were no longer so important, so the model started to suggest other things like gatherings and travel. Now, the biggest, surprise or success or phenomenon that was really interesting was India in March of 2021. We were here, this is March of 2021 in India, and everything looked okay. I mean, the cases had gone down. Maybe there was a little blip, but that wasn't anything that was alarming. But the models were going nuts. They were suggesting that the cases will be going through the roof. And we thought something was wrong in our models. By the way, we trained these models every night, overnight. So it was always adapting to what was happening in the pandemic. And the pandemic was changing. And indeed, the change here was the Delta variant. It came out, it had emerged someplace else, and I can't remember where it was, but we had seen the Delta variant, the models had seen it in some other countries. And now when we asked about India, it was seeing the same kind of initial blip as it saw in those other places and was predicting that, yep, this is what's going to happen. And indeed it did. But it was interesting that, so this is actually what happened. This is real data after, after March. And then here are our suggestions, the models suggesting what could be done. So if we really closed down India, we could have avoided that peak. And with some really careful selection of those restrictions, lower peak might be happening. So you actually have some choices. The decision makers can look at these predictions and make choices about which ones they like, how many cases they can live with. So unfortunately, we didn't have a red phone that we could call Modi and tell him what we were seeing. And that turned out to be difficult in general. The only case where we did actually have a suggested or effect on policy was Iceland. In August 2021, we were recommending actions on reopening the schools after summer. And we had actually, it's a small enough country, so we could really talk to the health minister and through a university researcher who had this access all the way to the prime minister. And as far as we know, they followed the recommendations and school opening was fine. Later on, what happened was Omicron, and we could not do anything about it. And that's because it happened everywhere at once. It was so quick that the models did not have the time to see it someplace else and then apply it. It happened as a kind of a black swan event. And that's the limitation of these kinds of models. They need to see data somewhere and then generalize it, and then you're okay. But if something like that happens, we can't really deal with it. But it's a very interesting study. We learned a lot about what can be done and cannot be done. And indeed, next time we have a pandemic, hopefully we are prepared and we can have these models all ready to go. And hopefully the decision makers would also understand by that time how to take advantage of them and could mitigate better than we did in the COVID-19 pandemic.
Absolutely. And just to theorize on some future applications, you can input different types of variables for a potential simulated pandemics or variants, transmissibility, lethality, these kinds of different things, and model those out as well, right?
Yes. Yes. So you can add information about the locale. That's what we did with Iceland in particular, because we worked with them and we got variables that were specific to them. And you can do a lot of that. We also done a lot of work with GPay OECD actually on combining multiple models. Some of them are very rule-based, and you can combine them with data-based models. And we have now an understanding how to calibrate them, ensemble them, so that we get more information than we would from just data alone. So that's possible. Another interesting effect is vaccinations. We did not really have that, but we didn't really even need it because the vaccination was reflected in the cases, and that was kind of a local variable that we could actually include. I think it was eventually included in Oxford data, but that was much later. So yes, there's a lot that can be done. Our test was really this data-based approach, predictive and prescriptive modeling, bringing them together. How much can you do? And it turns out you can quite a bit. I'm a little mindful of the time. I think I'm going to skip this live demo. I have it here, and you can actually go and try it out. It is an interface where you can select a country and then go back in time to some time, like when it was just happening in UK, for instance. And then you can ask AI to make recommendations, and you can edit your own recommendations and see what would have happened. So it's really quite addictive to do that. but we don't really have the time. I want to show some of the other applications as well. A little time that we have left, but I want to show something else, which also is very important for the society in this domain. So like I said, we built the X Prize competition together with the personnel at X Prize. They were really wonderful in putting together a competition. It was the fastest competition ever in X Prize. I mean, they started with private space flight, and now they have grabbing carbon from the atmosphere, feeding the next billion people, mapping the ocean floor, all kinds of competitions. And this was on mitigating the pandemic while it was still happening. We were kind of worried that it would be over by the time we have it. No, unfortunately, it wasn't over. But it was a very big success, I think the competition was. We had 100 entrants, over 100 teams. At first, we evaluated them, how well they were able to predict. And this was predicting the pandemic as it was happening at the end of 2020, yes. And then the second phase was creating the prescriptors. And again, testing in the data that hadn't even happened when they were building their models. And there were 50 teams at that point. And two winners were Valencia and Slovenia. Valencia was the actual winner, and they were really interesting. It was Nuria Oliver's team. They had been working with Valencian government in Spain all along, and they had somebody from the government in their team. So they actually had a direct line. And this is another success of this kind of approach, that they were listening to what this team was telling them. And Valencia did quite well in the pandemic because of that. But the interesting bit here is that in the end, we had 169 prescriptors that the human teams were creating. Some of them by hand, some of them machine learning, various techniques. So we had lots of expert knowledge in these human solutions. Now we can use that as a starting point to evolve further. And something really interesting happened, that here the blue dots are the prescriptors that the humans designed. And this is the same kind of a plot as I showed earlier, cases and stringency. And then we ran evolution on them. We distilled them into neural nets so we could evolve the neural nets, use Neuroevolution. So the initial population was human-designed neural nets, and then the final was evolved neural nets. And you see where the evolved neural nets ended up. They ended up as the Pareto front. Almost all the best solutions are evolution designed based on human initial designs. And this is further out towards its end than the population when we evolved it randomly, from random starting points. So your human expertise made a difference, but so did the evolution. And we found, even more interesting, that if you look at the initial solutions here, how good they were in the beginning and how much of their DNA ended up in the Pareto front. Like how good were the ideas in each of these dots. So most of the time, the best ones, the best blue dots, their offspring ends up, or their DNA ends up in the frontier. But there were these solutions that were really bad. Still, they had an oversized effect in the final Pareto front. Their DNA was there. So this is a way of taking advantage of latent potential of human ideas that haven't been completely developed. And this, I think, is fascinating, because this is a way of bringing people together, listening to their ideas, making synergies out of those, and doing better using AI. So this is a merging of human intelligence and evolutionary machine intelligence to do better for everybody. So there's a very positive story there that way.
Yeah, I think it's if I could simplify and clarify in any possible way, would be essentially thinking out of the box on steroids, where we're seeing, of course, we have our initial base of what we know already works, but just being able to see other solutions that we never would have otherwise, and seeing their impacts in ways when combined with our existing working solutions.
Yeah, and this also drives home the idea that diversity is really fundamental in discovering good solutions. Even diversity, when it doesn't look promising, can be promising. Parts of it can be combined with others and really realize the potential. And that's the big message from evolutionary computation, that diversity is the raw material that allows us to discover things that really work. Yeah, okay. One last topic coming up. What we did actually, based on the X Prize result, is to decide that we could really make this a platform that other people could use to solve future problems, not just pandemic, but other problems like maybe climate change or forest fires or food shortages, and make the software, make the technology available. And we call that the Project Resilience. It's backed by United Nations, the ITU, and also many other instances. And I'm going to have a call for action in the end, because it's a nonprofit community effort. We provide some of the framework, but we hope that people will come and they decide, they bring their problems, their data, and then can use this technology to solve other problems than what we've done. But the last example, really quickly, hopefully, is the climate change and land use optimization in particular, just to demonstrate kind of the range of different problems that we can solve this way. So there is quite a bit of modeling of the climate. And there's in particular this global carbon budget that's done every year, the fossil fuels and land use, and then absorption by atmosphere, ocean, and land. And there's like a balance that they calculate. And then we can try to optimize it. And one way to optimize is the land use. And there's interesting data available from 850, year 850, not 1850, but 850, all the way to just a couple of years ago, how land has been used all around the world. I mean, some areas more accurately than others, like UK, very accurately. And then we know, primary vegetation, secondary forest, whether there's urban land, what kind of crops, pasture, and so on. And all of those have actually a different carbon emission or absorption properties. And we know that too. There's a model called Blue, a bookkeeping model that it's kind of a simulation of how much actually carbon is emitted or absorbed with different usages. So now we have the historical data and we can estimate how they affect the carbon, and therefore we can train a model to predict. And that's some of the variables. Each cell, we know the area and what land was there, how it was changed, and then we calculate the emissions. So this is how we can train a predictor, and the predictor actually works. It makes sense. We tried different kinds. It turns out linear regression is not that good. There are some interactions that require something like a neural net, and also different parts of the world require different models. They work differently. I mean, obviously latitude in particular affects it. I mean, whether you are tropical or Arctic, it makes a difference. So we have to develop a bunch of models to make the predictions, but they make sense. I mean, if you take anything and turn it into a secondary forest, you are actually improving. And if you kill primary forest, you are, doing poorly. So this allows you to go from anywhere to anywhere and estimate how your carbon emissions and absorptions are affected. Now, the interesting bit that happened here, now, given that predictor, we evolve a prescriptor. How should you change the land? And here's kind of the progression, like the animation before, how we get a Pareto front that minimizes change, because change is expensive. Changing the land use is expensive. And we also want to minimize the emissions resulting from land use change. So we, again, want to go to the bottom left and gradually do. But it's interesting what was discovered. I mean, we know already that forest is really good. So what if we just make everything forest? At a certain level of change, at the same level of change, just make everything forest. And we thought that we couldn't do any better. There's a heuristic that should be as good as possible. And that's here. We called it the perfect heuristic because we thought it was perfect. But guess what happened? Evolution discovered better policies, better than perfect. Well, it turned out that evolution discovered that it could pick its battles. It would make a larger change where it mattered and less change where it didn't have much of an effect. And the total amount of change was the same. So it learned to pick its battles to a larger effect. Again, a really interesting strategy that evolution discovered we thought wasn't possible.
And is much more suited to human decision makers.
Exactly. Yes. Now, it's still hard to talk to human decision makers that you should plant some forest where you plan to do pasture, but it shows you what the value is. And again, don't have time for the demo, but you can go there. You can pick a place on Earth within this range and find what's currently done, what solutions exist, and how they would affect your decisions. But let's wrap up with the call to action with Project Resilience. So we are now developing many different projects. It's slow because it's all volunteers, although we have some buy-in from organizations like United Nations and so on. We have a current project in climate impact, which is more specific to various decisions that can be made, not just land use, but fossil fuels, and even factoring in things like new technologies that might come out, how they would allow us to cope. And there's another demo there on doing that that we don't have time to look at. Like there are actual scenarios that United Nations has set up, and we can evaluate whether we can actually meet them, how we could meet them. And again, a decision maker can then make changes and see how those changes could affect the outcome and the economy. So this is an interactive demonstration as well. It's a simulator by En-ROADS, a Climate Interactive, MIT, that we are plugging into in order to demonstrate decision makers how their actions would affect the climate. But the idea here is that you could take any one of the United Nations Sustainable Goals, they are listed here, and build a project resilience project around it. So we are looking at a couple of education projects. For instance, how do you reskill when AI is changing all the jobs? A person with a certain skills, what is available? How do you actually approach the reskilling and keep people employed? And we're also talking about food distributions when there are famines, climate disasters, wars. How do we actually optimize the food distribution so that we have least amount of hunger and cost? And this is the call to action. We really need more volunteers. We are building these projects. You can come up with your own project. That link gets you the Project Resilience website, where there's a real tutorial and then some suggestions for these projects. But you can get started. You can build your own team, address your own problem, or you can join an existing team and start building these solutions. So, all right, now it's time to wrap up this part. Anyway, so yeah, I believe that we're in a really exciting phase where we are making a transition with AI to from prediction to decision making with integration of these multiple technologies. And one of them is the Neuroevolution technology. It allows you to discover surprising strategies for decision making that help decision makers in all kinds of areas in society. And many of these applications are feasible now. We just need some buy-in from decision makers, but more and more of these demonstrations we build, the more likely it will be that that change will happen. And it may happen through United Nations. It might happen with your local government. It may happen just you alone, affecting something in a smaller scale and then scaling up. So please join. This is going to be quite a trip, and hopefully we'll improve the society in the process.
Absolutely. Thank you so much, Risto. And I know this will be extremely valuable for everyone in our community. For everyone listening, also, this is all going to be made available in the Better Society's membership and learn plans. And we will push as many people to join as possible because these are very important problems that need to be solved. Okay, Risto, thank you so much. Could you unshare your screen? And I've got some follow-up questions for you.
Yep.
Okay. So first off, to wrap up, what would you say are your top 3 lessons that you want people who are accelerating AI safety and solving these problems to keep in mind moving forward?
Yeah. Well, there are many aspects of it, but I think the excitement is by far the most important one, that this is your time. Now you can change the world. We have the tools, they are accessible. You don't have to actually write 30 pages of math or even read it. You can understand how these tools work and you can change the world with them. That's really important. It's not something to be feared. It's something to be embraced. It's something to be utilized. And no matter where you are, I mean, if you are a decision maker, if you are an engineer, if you're an educator, if you're a lawyer, if you're an artist, there's a way for you to be creative and take advantage of these technologies. So this is by far the most important lesson. Becoming proactive and exploring and finding new ways of doing things. It's both fun and it's impactful. So don't shy. There's no reason for that. Now, then second one is that we will keep developing better technologies. So if you are technically minded, this is going to launch careers, and getting into the education, getting educated is important as well, because the technologies eventually have to be developed by people who are technically minded, people who know math, statistics, understand complex systems. And there are more and more of these educational opportunities coming out. I mean, I've been involved with just making them available more broadly, but also like I just put together a Neuroevolution class for the first time ever, first ever textbook on it. And there are, of course, textbooks with LLMs as well, and other areas that are now popular. But these new technologies are important as well, other technologies. And that's the third one. Think broadly, learn widely. The idea is don't come up if you're looking at things very narrowly, just LLMs and nothing else. The ideas come from neuroscience. They come from psychology, maybe even social science. That's how we can understand something as complex as a LLM, because we understand how we analyze the brain and poke the brain and develop theories about the brain. Some of those techniques might be useful for understanding LLMs. And when you put together multiple LLMs, multi-agent systems, well, they work not that much unlike human experts, negotiating different perspectives and trying to come up with a consensus and decision. So understanding social science and decision-making organizations helps. So I think that this is important in innovation, is to have people who understand multiple disciplines and are curious about multiple disciplines. And that's where the next innovations will come from, combining these kinds of perspectives.
Excellent. All right, so I've got some questions from the audience here that I think will be very valuable to understand a little bit more about. First of all, how can organizations and government agencies get involved with this and start using this?
Yeah. Well, it does require this attitude of a little bit of boldness, in that you are embracing something new that hasn't been tried before. I mean, somebody said that nobody was ever fired for, I don't know, bringing Microsoft software in, or Oracle or something like that, because everybody else is doing that. You can always bring it in and nobody gets fired, even if it's not the best tool. So you need to be a little bit bold and see the opportunity and explore a little bit. And you need to have that leeway that you don't immediately get fired, or there's some patience in making things work. But those people who do, they will lead, the transformation. So I believe that the first step there is education and getting people excited. Decision makers are human, and they can get excited and they can get passionate about some techniques and developments and directions. Now, but you also have to be, when we develop these tools, you have to give them confidence. And that's where so much of our effort went, even in the COVID-19, giving them ability to explore and modify and interact and put in their knowledge and see the effect and have the confidence intervals and those kinds of tools. And safety now, absolutely. Safety is now emerging. We have to give tools that evaluate the safety and evaluate pitfalls, risks, and that technology also has to be developed. And then what's really important now, right now, most of those technologies are things that are add-on, but we have to develop these models and these platforms so that the safety is there from the beginning. It's integrated from the beginning. That's not yet happening, but I think people are realizing that we have to do that in order to make it possible for decision makers to use them. So it will happen in the next few years, because it's such an important thing to get into the system so that decision makers can use them. And you always have to also demonstrate value. So measurement, how well are we doing now? How well are we doing with the AI? That's a little bit better because if we're using technology like the surrogate modeling, the surrogate model will always give you an estimate of how well you're doing. So you have something. It's not real world yet, but it's at least a surrogate that gives you, if you do this, you expect that. And that is much, much better than just having to take a, leap and faith blind. You have some idea what works and what to expect.
Absolutely. Yeah. And I think, to stress that point, it's actually very misaligned incentives with these giant AI companies right now, where safety is important, but corporate profit tends to take priority. And so having that baked in is crucial, which leads to one of these other questions. What are the challenges or the main obstacles to implementing neuroevolution solutions in the real world scenarios?
Oh yeah, I know a lot about that. I mean, tried to do that for so long, and we talked about this indeed, making the innovation palatable to people who are responsible for making these decisions and incorporating new technology. But a lot of times we have found people who are really passionate and they want to bring it in. But then within the organization, you still need to get the data, right? And and that's been a problem, that the data does exist, but it's siloed. Part of it is here, another part here. And it sometimes has taken 6 months to just pull the data together and clean it up and understand it. Everybody has data, but it's not yet usable. And it's getting better. And actually, Cognizant has a whole direction. And a couple of years ago, that was the main direction, is to make the companies actually utilize their data, get their data, and make it available. It's a transformation into data. That's largely happening, and it's not completely there yet. But that is a big obstacle as well. If we want to personalize these decisions, we need to have personalized data. So that's one challenge. That I think would be still the current one. Now, but I think that you pointed out safety, and I think that's the emerging one. That now once we have data, we actually can build it, but it's still a little scary. We have also the estimate of the value, great, but do we have an estimate of the risks? And I don't think we do yet. And that's the next challenge that will have to be built. And it's just incipient, it's just starting. Now, you mentioned that it's hard for the big companies to pay attention to it. Well, if you actually want to sell your AI solution and have it adopted, you got to pay attention to it. It won't be. You won't make money unless somebody adopts your solution. And then it has to address the safety issues for it to be adopted. So I think it will happen even with the economic forces that we have at play.
I agree, and it's certainly a matter of time. I'm hoping that companies will see, and I will say Anthropic is the leader in this so far, but we'll see that taking a stronger stance on safety as not only the right thing to do, but also a corporate and branding strategy is a good decision economically. And now we have a couple of different questions. I'm paraphrasing to fuse a couple that are quite similar here about AI safety, but there's a lot of questions about the ethical implications. So as neuroevolution enables the creation of complex AI behaviors, what measures do you propose to ensure that these systems align with human values and societal safety?
Yeah. Well, the first answer is that we still are in control of the objectives that we are optimizing. And that means that you have to understand what it is that you optimize. Like, okay, for instance, we did another application on, well, I mentioned actually the diabetes. So a patient comes to emergency room with a diabetes shock of some kind, they are medicated and they go home. And we are trying to come up with medication so they wouldn't come back. Now, a really good way of guaranteeing that is to kill the patient. They won't come back, but you miss the objective that you want to keep them alive and still not come back. So sometimes that's a very extreme case, but there are sometimes side effects that are not part of your design. You didn't think of it. It's not part of your objective, and you might cause undue harm that way. So when you are thinking of what you are optimizing, you should think about also there's always a cost variable. Every time there's some kind of a cost. What goes into that cost? Or maybe in treatments, there's the patient recovers. What kind of side effects do they have? What's the quality of recovery? The speed, completeness, and the quality, and also the cost of the medication or the cost to the patient. So there are multiple objectives, and you have to think about what needs to be included in it. So that's the first answer. Now, ethical implications is a really big topic, and what I really like about it is that it used to be philosophy, right? And when we ponder about philosophical implications of things like, the trolley problem. I mean, people have talked about it for decades, and people have talked about what is real and what is the truth philosophically. But now we actually have to develop definitions that are actionable for them. We have to solve the trolley problem with the self-driving car, you know. And when we are talking about LLMs, the question is, are they telling the truth? Well, it turns out truth is not that simple. It changes over time when we learn more and the world changes. Sometimes the truth is there to a degree, and we have to actually rethink what it means to be truthful and trustworthy. So I think it's wonderful that it's like a real jolt to philosophy, that now you actually have to be actionable philosophy in your philosophy. And we have to develop new philosophy because of that. And that concerns ethics as well. The ethical theories will have to be actionable. We'll have to program them up. We have to put them into these models. And that needs to be developed. And that's like a real shot in the arm of a totally unexpected another field. And it needs to be developed. I don't have a solution, but I know that there are lots of people who are thinking about it.
Absolutely. And for those listening who haven't heard of the trolley problem, it's essentially a philosophical, ethical thought experiment of a trolley moving in two possible directions, one that would kill one person, one that would kill 5 people, and you, being the person at the switch, can decide whether the trolley hits 1 or 5. And then there's multiple different variations of that to change how people would make that decision or not. And so, yes,
Yeah,
self-driving
and
cars
also,
are. Mhm.
when I emphasize here, it also depends on your culture. Like some cultures value people who are old, and others value people who are young, and that determines which way you would go if you have old and young people, for instance. So again, there's not a single answer. It depends on so many different factors, and we have to be able to somehow incorporate those into our decision making.
This is something that I could see these neuroevolution strategies helping with, right? Because if we can put in, even right, for different jurisdictions, and some of the questions that I get a lot are, how do you value the different ethical and values differences between not only individuals, but countries, cultures, as you were pointing out. And certainly there are some ways that we can find a unifying direction. I know Brian Johnson has shared his views on the Don't Die movement, and that if we can quantify optimizing health span as at least one direction that most people would agree on, where you don't want to die as one of the primary objectives, that is at least somewhat unifying. But then, yeah, of course, if you're making different decisions in a collectivist versus individualistic society, or certain religious societies, then you want to be able to plug in different variables and see how that works. And I see that with this neuroevolution approach, you can optimize for your specific situation and see how, if you were to play it one way, that would differ from another way, and make the most informed decision for you and the people that you're governing.
Yes, exactly. That's exactly the idea. Yes.
Okay, so we have some more questions here. We can maybe do another couple before wrapping up. So I'd also be, there's a lot of these that I'm also wondering about, I think would be really interesting. How do you envision neuroevolution integrating with the other AI technologies that are out there today?
Yes. Well, I did show that one integration in the Neuro AI model where Neuroevolution is in the center. That's the core. That's what's discovering the decision strategies. But but the other technology like LLMs, Gen AI, can help you to pose the problem for that you're trying to solve. And if you go to an organization, you don't necessarily know what you should do. I mean, it might be to minimize cost, it might be maximize customer satisfaction, or something else. What are the opportunities where better decision making can help? So that's one. And then also, when you're collecting the data, you can get a preview from an LLM what the data might look like. And then we actually get the data, you can augment it, you can fill in missing values, you can improve its quality and overlap. So other AI technologies make it much more possible and easy and viable to deploy neuroevolution in the real world. And same thing in the other end of actually making the decisions. You can have an LLM, for instance, to evaluate the impact, evaluate the biases, evaluate the risks, indeed ethical considerations. And you can also have them maybe even deploy the actions through text or some kind of user interface. So I see especially Gen AI as technology that makes it possible to deploy things, identify problems and then run with the solutions. But there are other technologies as well. Another one that I did mention, I showed, is the rule set evolution and rule set representation from long ago. I mean, this is from, I don't know, 70s, 80s, something like that. You are expressing behavior in terms of logical rules. Now, there are ways of, even if we have neuroevolution and we evolve a neural network and it's opaque, you can evolve a rule set system that duplicates its behavior, just like we did in the X Prize competition. We took all those solutions, all different technologies, we distilled them into a neural net. Well, you can similarly get a rule set expression of the same behavior. And now you can look at it. And if you can look at it, you can edit it. You can identify biases, you can fix them. You can identify things that are missing, and you can add a rule. So you can bring in other types of expertise when you have a rule set, and generally it's explainable. So that's another synergy of two different technologies. One explainable, editable, safer in some sense, and then one really powerful because it discovered really good decision-making behavior. And we can imagine other combinations like that. Well, also the confidence intervals. Well, that's statistics, bringing in statistics of Gaussian processes in order to model the trustworthiness of a machine learning system. So there are numerous synergies like that, and we're discovering more all the time. And there may be still others that we haven't even discovered. But the point is that in order to deploy something, no, it's one thing to be a tech demo and another one to be actually an application that really works in the world. And that's why we need these other technologies to serve as interface and serve all these different needs that need to be met in the world.
Yeah, I think it's amazing to think about the potential implications with, an organization like the UN or others coming together, or institutions globally pooling all of that data and then having an LLM or some type of UI that's super simple and easy to interact with, but that's pulling from that evolutionary strategy to bring all of that data together, but with simple user prompting, be able to understand what is the optimal solution that you're really looking for and refine that prompt to eventually pull from all of these data sources and come up with, the best solution that can then be shared to decision makers at the UN, presidents, mayors, etc. And yeah, I mean, that would make a huge difference very quickly.
Yeah, and I'd like to emphasize something that we've been talking about all these technologies. I mean, LLMs can do a heck of a lot. I mean, you can even ask them to give you a decision strategy. But what we're looking at here with Neuroevolution is the really novel discoveries, things that you might have missed. But LLMs won't do that because LLMs are trained with everything we already know. We know, they are interpolating between things that we already know. They're not ever going to be that creative. which evolution is, because it's doing this exploration in a much bigger space, and it can discover things that you wouldn't even consider. Nobody's ever written about them, about having sun up 24 hours, for basil. So that's the core of it. It gives you this exploration that gives you solutions when they're really hard to find, or when you need a different solution, a surprising solution. And that is what I like a lot. That's what gives me the excitement that this is we're onto something.
Yeah, totally. Okay, so we'll do 2 or 3 more and then wrap up. What are the key topics that your upcoming neuroevolution textbook will cover?
Yeah, well, so it is a couple of things. I mean, it is a comprehensive summary or survey or exposition of everything in neuroevolution, which means using population-based search to discover neural networks. And that means primarily behavior. So agents that behave, they might be robots, self-driving cars. They might be agents in a virtual environment, video game characters or simulation characters. Or they might be animals and understanding their behavior. So behavior is one. Another big dimension is optimizing architectures of neural networks when you are doing deep learning or even LLMs. What are some of the architectural choices that we could have? Humans have real hard time defining something as complex as a deep learning network or an LLM. So we could use automated methods to devise the architecture and then use learning, machine learning, gradient descent on that neural network. And then there are combinations of techniques, like you could combine reinforcement learning with evolution. So you have a whole society of individuals that learn during their lifetime, but they also act as a population. And you have both the discovery and refinement. One of the most interesting combinations is indeed LLMs with evolution. And there are 2 different directions. You can evolve LLMs, or you can use LLM to implement evolution. So you ask LLM, here are 2 parents. What is the offspring? And now they can be bit strings, they can be pictures, they can be poems, they can be anything, because LLM can understand those. But it's still an evolutionary process, and there's crossover, there's mutation, there's selection upon variation. So that's a very modern, new kind of a approach. And then this whole area of biology, trying to use neuroevolution to understand biological principles. So it goes all the way from why do we have this circuitry in visual cortex or someplace else in the brain? Where does it come from? What are the constraints? Why does it emerge like this? And all the way to behavior in animals. Like, for instance, we did a study on hyenas and why and how they can team up to steal a kill from lions, when lions are much stronger and can easily kill hyenas. But if you have 30 hyenas that all move at the same time, completely coordinated, the lions will have to flee and they get the kill. And this is much more sophisticated than anything else that hyenas do. So we may be looking at an evolutionary breakthrough in biology, and we can model it with neuroevolution and understand where it's coming from. You need certain level of boldness, you need certain level of safety, you need innovation, you need some altruism. What are the ingredients for this evolutionary breakthrough to come about? So it's a biological hypothesis that we can shed light on using evolution. And eventually, for the future, in science, I think a really interesting big challenge is evolution of language. Finally understand how language came about in humans, and only humans. I mean, we have maybe Coco the gorilla and some chimpanzees and orangutans that we can train to communicate with symbols, but language like a grammar and the whole structure of linguistic primitives and combinations and rules, it doesn't exist in anything else. Where did that come from? Was it need to communicate in displacement of space and time? Was it cognition, symbolic thought? We can build or we can test hypotheses using neuroevolution. We need a really good simulation and manipulating constraints of societies, and in a complex world where there are shortages of food and maybe predators and others. But we have the computing power now to start building something like that. And we have the learning technology like Neuroevolution that could actually give us that behavior. And we might finally understand what made language emerge in humans. And that would be really, really fascinating scientific age-old problem that we could finally get light on. So that's all in the book.
Absolutely. That's super, super interesting. Okay, one more. How do you see this? I'm piecing together the work of NVIDIA Health and the Arc Institute mapping the human genome and essentially sequencing everything from DNA, combining with this neuroevolution approach where we could theoretically map out every possible genome, every possible mutation, and see through this strategy what emerges as the optimal disease-free health span enhancing combination, and then theoretically also be able to edit through CRISPR technologies or others like that. Is that something that you're thinking about, and how would that be applied for health span or health tech?
Yeah, well, that's still maybe a step beyond the evolution of language, but because one thing you probably need a little bit more a better understanding is the functionality of genes and especially the interactions of genes. I mean, we have, of course, the whole genome, but we don't really have a functional map of how they interact through proteins and other genetic regulatory networks. But it is starting to emerge. I mean, we can implement genetic regulatory networks and see the effect of these secondary phases. I think if you talk to a biologist, and I sometimes do, that we are really evolving just the DNA. We don't really know anything or incorporate anything in our models about genetic regulatory networks, which is where probably most of these functionalities emerge from. Why does this DNA, why is it active in the spine but not in the hair? I don't know. I mean, things like that are all in the genetic regulation. And we should understand it and put it into the models. But it is emerging. Now, one important point here, though, is that what made AI happen, like I said early on, is the compute, the scaling, and the data, of course. But really the million times and then another 40,000 times more. That's what made AI happen. It made neural networks work as deep learning. It made language models work as general knowledge engines. We haven't done such experiments yet with evolution, taking advantage of that level of computation. And this is what could be done. And what you just proposed might be this kind of a touchstone problem for scaled up evolution, that we could actually evolve not just language in a big simulation, but actual complexity of the DNA in a genome. Maybe not starting with humans, maybe starting with something much simpler, but actually replicate how evolution actually progresses and discovers these structures and how the regulations work. And I think we are there. I mean, we could start working on that, and some people have already, and expand on that. And it could then have huge implications in health, absolutely, to understanding, not just to understanding, but also repair of something when something goes wrong.
Amazing. Thank you so much for taking part in this interview. You shared so much value for our audience. Where can people get in touch with you or follow your work?
Yeah, so we'll post some links. I hope in a website, but I do have a website in my academic website, NNCSU Texas EDU, and there's all the papers are there, and also we have in CALE, Cognizant AI Labs, where a lot of this research came from, and that is evolution.ml. We have multiple links to pointing to that. There's demos, there's software, and lots of resources. So we try to make everything available. We strongly believe in open source. We strongly believe in openness and people building on other people's work. And also the Project Resilience website, which is also linked. There's a GitHub site where you can get started. So we'll post all of those links, make them available, and you can take a look.
Brilliant. Okay, everyone. We are going to put all of these resources together for our members and in our free community. You can join. Thanks again, all of our listeners. Be sure to follow up with Risto. and download the slides of his presentation. We spent months vetting these speakers because we knew they'd be really valuable to you. So definitely check them out and follow what they're up to. And if you could support us, if you enjoyed this episode, please share this content, smash that like button, and sign up for our newsletter. Share these masterclasses with your friends and your favorite speakers so we can have them on. Tag us on your shared posts to get exclusive perks like our member community deals on merch and early access to surprises. I promise we'll make it all worth it for you. Risto, thank you so much for taking the time.
Yeah, thank you, Adrian. Thanks everybody for listening.